Okay, so you're welcome back to episode 18 already. Just a quick shout out to everyone that has subscribed and to all those who have bought coffees and all that on the links. Thanks a million for that. It means a lot and supports the channel. But on to the job in hand. As you can see, there's nothing on the bench, new brown paper, and just a marker. So anyone that wants to see Formula One parts in their flesh, as many of my videos have covered before, you should probably tune off now or turn off now, because this is strictly going to be just a kind of a dialogue, just talking about tolerances, how the engine is built, and all that sort of thing. Now, I had all this recorded already and I had to delete it because, or not delete it, but not post it because which you'll see in a moment, I brought in the laptop and it showed a build document, um, and unfortunately I hadn't it covered with my hand properly and it showed the manufacturer. So obviously I've got a lot of documents here for building Formula One engines, and I don't really want to get into trouble um, with those. I respect all the manufacturers obviously, but I just want to play it kind of, cautious with what I put up on YouTube, what I've paid for in terms of documents, what I've got sent to me by clients in terms of building engines and all that sort of thing. So I just chose to delete it because I don't want to get into that sort of, not NDA but copyright or proprietary material risk. So that's why the video has been delayed for what, a day and a half or 2 days. I just chose not to post it. But let's do it all again, and here we are. So as you know, a Formula One engine is it's an engine for a start, like other engines. It works the same pretty much. You've got fuel, air, a spark plug, and a bang. Now, this engine here, which I'll be talking about, is concerning the V10 engine, which I think is probably the best. You can debate that, like you can say the new ones are better, whatever you want. Um, to me, the V10 or the V8 afterwards, or indeed the V12 before that, were the best engines because they were very pure. They ran, naturally aspirated. There was no turbos, no electronics. As I said before, countless times, the new engines are called power units. They're not called engines. They rely on, regen, all that sort of thing, which I don't really want to get into. I'm not that interested in. Um, Now, however, if I got the opportunity or bought an engine, a new engine like that, um, I would cover it, but it would be only for the sake of covering it. It's not my passion. My passion is in the V10 and the V8 engines, as you probably gathered from if you've followed my write-ups online for the last, I don't know, 10 years. You've probably gathered that. So it's just a very pure way of making power. Fuel in, fuel out, no turbos, no electronics, nothing like that. So fairly simple, and as I said before, something we'd probably never see again. So let's crack on a bit. So to start with, I've got a billion emails about this and messages. So the Formula One engine, when it's cold, um, you'll probably all laugh that it's lock solid. It's totally solid steel mass, aluminium, titanium, can't be turned. That's all complete and utter nonsense. Um, I have no idea who came up with that. It was probably, I don't know, someone that watched Top Gear that loves Instagram, and they posted this video that it's lock solid. I watched all the videos and it can't be turned until it's at 95 degrees C. Total nonsense. Um, the engine can of course be turned when it's assembled. Now, like everything else, it's not a good idea if you've got, um, you know, you know yourself, if you've assembled a lawnmower, a rally car, your own car, a high performance car, a Formula One car, anything like that, a simple machine, you don't really want to put it into action until you get it up to temperature, or until you circulate the oil or be sure the oil is moving. Now, that's the exact same with a Formula 1 engine, in that all those things apply. It can move, shock horror, when it's cold, when it's dry, but it's not a great idea, because with an F1 engine you want to take every chance you can, or take every opportunity you can, to not ruin your bearing surfaces. Now that would apply especially to the hydrodynamic bearing shells, which I covered before in, don't ask me what episode. But basically you don't want to be scraping stuff, when it's cold. You don't steel on steel. Now, in terms of tolerances, which might surprise you and I'll cover later, they're not awfully indifferent to high performance cars nowadays, or even going back, many years, 30 years, which we'll get into in a moment. But the main thing with a Formula 1 engine, the engine really is secondary to what you see on track or what you hear on track. There's a huge amount of build information, of backup, of data, and all that sort of thing, which we'll delve into in a moment. But you can probably imagine it's vast. In terms of the machine parts, like in manufacturing, in DFM or DFA, which is designed for manufacture, designed for assembly, in a road car engine, your parts would be coming off the production line that have a certain tolerance, and they would fit with other parts, and so on and so on and so on. And overall, when all those parts are assembled, they would make a fine engine, or make an engine that's capable of output at advertised figures. Now, with an F1 engine, because it's so highly strung, they have to keep a very tight check on tolerances. Now, for those of you that aren't into tolerances or know nothing about them, let's cover that very briefly first. Again, this video I had recorded previously, as I said, but there was a small bit too much information in it, and I was just afraid of not getting sued, but just respect to the people that I know in the trade, that I work with, or that have sent me these documents, and I don't really want to share too much information. Now, you've watched many videos on YouTube before. There's guys on there saying they don't want to share too much information. That's because they haven't got it. But trust me, I have all the information right here, which I'll show you briefly in a second. But it's just about respect, and it's about informing you enough without me getting in trouble or breaking that friendship, which took 10-12 years to build up. So just giving you a small sniff of what's involved, without giving too much away, and you going away with knowing all you need to know, and me being safe, basically. So let's just cover tolerances first. So again, no parts on the bench. Surprise, surprise. New brown paper, plenty of space here for writing. So the machinists that watch this channel will know well that tolerances and limits and fits and all that sort of thing. So let's cover that briefly. So if you want to make any part, from a simple part, let's say, I don't know, a part for your lawnmower, or a part for a hinge in your kitchen or something, you measure it yourself and you say, okay, I need a shaft that's 5 mil in diameter. So let's say this here is 5. Okay. Now, if you send that to a normal machinist, he's going to say, right, this guy has no idea what he's talking about. I'll just make it 5 millimeters. Not spend too much time at it. 5 mil, he'll be happy. That's fine. But if you get a drawing from an engineer, let's say in agriculture or whatever trade, he might have the same shaft drawn like this, and it'll be 5 millimeters here, and it'll show a tolerance, okay, of, let's say, what? Let's say plus or minus 0.1 millimeters, okay? So what that means is this guy that designed this shaft, who is, let's say, in agriculture or marine or whatever you want, so this guy wants this shaft back. Now, one point to note, if you apply standard tolerances on a software package, it'll automatically put the tolerances at 0.1 mil. Now there's various other tolerances it'll output without getting into too much. Whatever trade you're into or whatever level of design engineer you're at, you will know that you can apply, when you export the 2D drawings, you can export in 0.1, 0.01 or 0.011, or it'll be specified then after that to another tolerance or a reference to a datum surface. Let's say if you had this shaft going up here and there was a flat surface here, you might have a specified tolerance between here, the diameter of this shaft here, and this surface here. So you can specify all those, but for the moment let's concentrate on this one here. So the marine or agri engineer has specified this shaft. He wants it 5 millimeters with a tolerance of 0.1 millimeter. So what that means is this shaft will work or be correct if it is 5.1 millimeters or 4.9 millimeters. So you can see the 0.1 there. Obviously 0.1 from 5 is 4.9, or 5 added to 0.1 is 5.1. So this shaft will be correct if it's either of those two sizes. Now the thing with this is there is a, let's call it a stack up or an overall tolerance of 0.2 millimeters. So obviously that's fairly easy to subtract there. So this shaft can be correct if it's 5 millimeters in diameter. Perfect, brilliant. The machinist hit it right on. He had a low stress day, simple shaft. He looked at the tolerances. They could be 4.9, which is ginormous for a machinist, or it could be 5.1. Happy days. Now, if this shaft was specified at this one here, which is 0.01, the plus and minus is 0.01 below or above, so he had to be a bit more careful. Now, if you're getting into this area here, he had to be really careful. So that's kind of top level. Now, obviously, there's more after that, depending on, you know, what the part is for. If it has to have a lathe turn finish, if it has to be ground, if it has to be burnished. Also, what has to be kept in mind is the overall finish of this shaft and the straightness. If it needs an aftermarket coating like a anodize or a DLC, when you're getting into this area here, anodize would increase the shaft diameter, or DLC or whatever like that. So the finished shaft will be checked off the engineer's drawings with this tolerance here, the plus or minus. If it passes that, fantastic. If it doesn't, it fails. It goes in the bin. So that's a kind of a brief rundown on tolerances. Now, with the Formula One engine, as you can imagine, the tolerances are, you know, very, very, very tight. I'm not going to use terminology whether the tolerances are tight or small, big, whatever you want to call it. We'll just work in figures. So if you want to machine a job which is a crankshaft, let's just go single throw. Can you see that? Where we go? We have to get more brown paper. So if you've got a crankshaft here, with the throw on it here. Come down here again. And across here. So this will be your PTO. Doesn't matter, but let's draw it that way. These would be your main bearings here and here. So mains and the big end. So with this particular engine, which I'm going to talk about now, which I have to be careful on how I'm going to describe it. Let's call it a V10 engine made east of Ireland. Okay, not too far away. So that should give you an idea. But so with this engine, the machinist has got this drawn. He's got tolerances for the crank throw, which will be this distance here, here to here. Okay, so that would be the throw, and the stroke then obviously would be twice that. So that would be the full reciprocating motion. So the engineer or the machinist has got this call out, which would be at this level or down here at a further level. He's got that call out to work to, and he has to machine it to that tolerance. Now he does that perfect, it's within tolerance, and this could be, let's say the part is specified within what, let's go what the figures are or near them, without getting into too much trouble. Let's go, the throw is 21.285. okay, so that's max, and the minimum is 21.1262. okay, so that's the maximum and minimum tolerance this can be here. Now you should know that the tolerance, it can be anywhere between here from this little example here. So this is the exact specified tolerance of the V10 engine I'm talking about. So 21.1285, 21.1262. Now obviously this will be a ground finish. After this has been machined, turned down on the journals, heat treated and ground, this is what they need to hit. So taking that into account, that passes. It's between the two tolerances, it's perfect. So the ideal tolerance would be halfway between those. Let's just say what, let's just call it 1270 for a round number. So 1270. Again, this is going to go really out of hand, but you get the idea. So 21.1270 has passed, perfect. The quality control has checked the crankshaft, brilliant. It's all in spec, grand. But what needs to be done then is the crank has to be checked what it actually is. This figure is then, like, it's checked on a jig. You know, the crank is put in here. There'd be 10 throws, etc. There'd be a dial gauge down here. You have your clock here, and you take the maximum throw of each journal, each individually, and your average tolerance is measured on each journal all the way across, for 10 or for 5, whatever you want, left bank and right bank, and that's entered into a ginormous database. So the engine build database is something that's not spoken about too much, but it's half the engine design feature or work. So once you've got the crank entered into the database, you then enter the you then measure the conrods. So the conrods go into a jig, same again, they're machined, checked within tolerance. They're then checked what tolerance they are, you know, up or down, whatever. Now this particular engine, the maximum and minimum tolerances were, where will I write this, over here. So they're titanium conrods, as you know. There are, the maximum was, this is all off my head, I haven't got it wrote down usually. I usually have, but I don't have today because it's the second time around. They were 101.325, and from memory the minimum was, or the maximum, sorry, was, the difference was, okay. So this is, once again, now there would be a stack up in the conrod. You've got to put in your bush, the silicon bronze, aluminium bronze bush in the small end. So there would be a lot of stack up here. They would be then bored, you know, hone bored. The big end would be bored. The small end then would be honed on a Sonnen conrod machine. You've seen them on YouTube. If not, Google them. They're called Sonnen conrod, I don't know, boring machine or grinding machine, but they're ground very accurately. There's also another stack up in these two figures, in that once you hit the big end and the small end diameters successfully, they both have to be a certain distance apart. So you've got small end, big end, and distance between them. They also then get entered into the database. So there's many figures already, you know. Now, moving on from that, you've got the engine block. So the engine block would be like this. Where am I going here? Over here. So the engine block in a V10 will be like that. Come up here. You all know them. The V would be here. Come up here. That's terribly bad, but you get the idea. So this is the right hand fire face and the left hand fire face right here, and there would be a dimension between the crank center line and here. So again, once this is all machined, you enter this into the database. That's a dimension, that's a dimension. It would have tolerances plus or minus, and that gets entered in again. And just to go back to these tolerances here, which I get a lot of questions of, the main journal tolerances on a Formula One engine are not that tight, would you believe it? So on this engine here, which we're talking about, so the crank mains, the clearance tolerance on these mains is, listen very carefully, it's not locked solid, it's 0.025, okay, 0.025 minimum to 0.0508. All right, so to me that's pretty standard clearance. Off the top of my head, in a, let me think, what car that you'll probably all know. Let's think of the American guys as well. In the Rabbit, the Golf Rabbit, you had the KR. I'm not sure if you had the ABF. In the States, you possibly had. So the KR, I know this religiously. The KR main bearing clearance was 0.04 to 0.06. Again, this is millimeters, okay? So that's KR, sorry, ABF. That's the 1.8 Golf Mark II GTI engine, and later on the Mark III Golf 2-litre engine. Now they had different stroke. The ABF had a longer stroke. It increased the dwell at top dead center because of the longer conrod, and that measurement I can't remember. The KR was 144, I think. The ABF was 159, was it? Maybe, possibly. But the big end clearance 0.04 This is a bog standard mass produced car, 0.04, 0.06, with the F1 engine. Let's write it down again. It was 0.025 to 0.0508. So let's just pretend we're blind. It's halfway. The Formula One engine big end tolerance is halfway between the KR and the ABF VW engine. So these engines are not lock solid. Like it's total nonsense. They're fairly common in terms of tolerances, but what matters mainly, as you've probably gathered so far, is the stack up calculations between each part. They're all measured absolutely perfectly and entered into the database, and it spits a figure out, which I'll cover in one sec when I pause the video, because it's at 26 minutes long now, and I shall talk to you in one moment. Okay, so we're back after that quick break. So if all those people that have told their mates down the pub have left already that a Formula One engine is lock solid when it's cold, sorry about that. Hopefully you'll come back later on or watch this video. But to those that are still watching, the 5% that are still hanging on, let's go a bit further. So I've got more paper, new paper. So when you've got all that done, which you've seen already, obviously you'd put all these into the database on the engine build file. It would spit out some numbers. You'd build the engine then, and you would mount the cylinder heads and then check what your piston is doing at top dead center. Now, with all those checks, the piston should be the piston and conrod, as you know, looks like this. So that'll be the conrod, and the piston would look like that. So when it's all mounted in the engine, this height here is then measured with the dial gauge down through the cylinder head with a probe, actually with a dial gauge like this. So your standard dial gauge, you've seen them before. Now this one is particularly fine for checking Formula One engines. It's got the stylus here, and you can see the various measurements there. So it's really fine. Like if you breathe on this, it will move. So that's the weight of the marker there on it. So very fine dial gauges are used to check the compression height here in relation to the deck, and the height here to here, which on this particular engine that we're talking about is can be, sorry, should I say, 19.87 to 20.1. So that's the type of tolerance you're dealing with there. It's very small, and that is, sorry, not to be confused with the height the crown goes in relation to the deck face. It's just the height the whole assembly is from here to here. So from the center line of this axis here to the deck face. Now if the piston, when you've measured all this, if the piston is coming out over the deck face, which I'll cover in a second, the piston is sent back to the machine shop and machined down off the crown. Now the piston wouldn't be exactly like that. It would be like that and that, with the eyebrows for the valves machined out, and the valves would go up there like that. Now again, these tolerances, even on the eyebrows, the tolerances from the valve face to the eyebrow cutouts are checked. These are a defined measurement again, entered in the database, which involves building the whole engine up, checking with the dial gauge what the valve moves, what your tolerance is here, and they're noted again, and the database will spit out a measurement. Sorry, you're a bit, let's move you up there. The database will spit out a measurement of what this should be here, crown clearance to here, and the overall clearance from here to here and from here to here, which is your stroke or your throw. Now, when the combustion chamber volume is computed or gathered, it's a known number, but it may not necessarily be the protrusion, height here to here. So that's why the piston is sent back to get the protrusion heights the same on all cylinders. Like it'll be 5 here and 5 here, and that's then a known measurement. Again, entered into the database and computed and sent back to the overall squish height, which is the distance between the piston crown, once you've got them all the same, and the combustion chamber roof, which would be like that, not like that, but this volume here. So these are all tailored, they're all moving the same. This is the same height in reference to this. This is the same to here. The crank is the same. The database is confirmed they're all the same. Now again, these will be picked from batch numbers as they're machined. You might machine, let's say 50. You'd pick and choose what ones are nearest tolerance. You wouldn't necessarily bin them. You just pick the closest groups of all the conrods for each particular bank. Your last point of reference then for your compression governs is the thickness of the head gasket. Now, the head gasket is something I'll get into in another video, but generally it's some engines, like going back, way back, were your common head gaskets, which you'll be familiar with. But in this particular V10 engine, this is a stainless steel head gasket, which will be the same thickness as you know, a bean can or a beer can. I won't say credit card, it'll be way thinner than that, but its nominal thickness would be about 0.25 millimeters, or a range from 0.15 to let's say 3, depending on what your database sends out here for the stack of tolerances. And you would then insert your head gasket here, which on the V10 looks like this. I'll try and draw it. It's going to be fairly complex. So to go along like that, it'll have a cutout here, here, and here, and it'll be really thin all around here. You get the idea. Around here, here, and here. So the gasket only lies just around the chambers. The oilways, the waterways, all that sort of thing are sealed with O-rings, and the head actually sits the thickness of the gasket off the deck face, which would be, this would be the block. The head would be up here, but they're actually separated. Which, moving on to that, which I'll cover in a later video, why cooling is important. There isn't, this is all these surfaces here sit off the deck in relation to the head gasket, or the cylinder head face. So the head gasket is just squeezed on its surface area, and these are O-rings here for oil, water, coolant. Coolant is water, but you know yourself. Oilways, coolant, and then the blast face is covered with just a flat. It's just a flat. It's not like the MLS head gaskets we see now in cars, which would be a one gasket here and a thinner one then here like that, and one below it like that, and these compress down to form the seal. Anyone that has turbocharged an engine, you know, you've taken apart these MLS gaskets, you've taken out the center layer, which would be about 0.8 mil thick, and you've just used these two layers for extra compression. But a Formula One gasket isn't like that. It's just one thin strip, and it's torqued down. Now, generally, with torque values, which I'll cover later, possibly, you've got a bolt here, 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 and here. So these would be all torqued the same. These ones here, because they're covering, you know, one cylinder here. In some Formula One engines I've seen, not to mention any brands, but going way east, out to the leg with Sicily here, somewhere here, these ones can sometimes be half the torque value of these here, just because they're not supporting an adjacent cylinder here, so they're only holding down half that combustion pressure. But I could go on for ages with this video, but that's kind of a basic rundown on how they're assembled. It's generally taken serious note of what the machinists hit off the machines or the grinders, entering all that in the database. Like, it's called blueprinting now on, you know, if you were building an engine for your own car, it's generally called blueprinting, but I mean, that's not even half of it when it comes to a Formula One engine. This is a whole other level here. It's taken everything into account. Entrant in, like, the database is basically a spreadsheet which spits out, yeah, okay, that's another number, move on, move on, move on, and then you're finished with, you know, X, Y. So you have to hit that target, and that target here would be finishing up in the combustion chamber and the cylinder head gasket height. Now again, in the cylinder head itself, the tolerances for the camshaft in the journals, it's nothing obscene. A tiny bit tighter than a normal road engine, but nothing too crazy. The only reason people think that, or have been taken in by the myth that the Formula One engines are lock solid when they're cold, is, I think, because they've just seen videos of arseholes posting other things, or you know, viewers seeing engineers heating up the engine with hot oil and all that sort of thing, hot coolant. The only reason they use hot oil, which in this engine here, the specs are, I think, 55 degrees. You'd pump your coolant around at 55. You'd circulate the oil, obviously with not related to the engine, but you'd pump your hydraulic oil as well for all the throttle actuators, the gearbox. You'd circulate that around as well. You'd make sure there's no airlocks. You'd bleed it off, which is easily done. The only reason that's done is just to save the engine from turning over when it's cold. As you can imagine, like everything, you know, you've seen YouTube videos of guys starting engines or motorbikes and revving them out to, you know, red line when they're freezing cold. It's just not good. It's not something you do yourself if you're an engine guy. But some people get sucked into that myth that it's lock solid. It's absolutely not. It can turn fine, but with Formula One stuff, you don't want to risk scoring various journals, or, you know, hydrodynamic bearings, which we covered before, just general stuff like that. You don't want to risk scoring that with cold oil or with lesser tolerances, not tight tolerances, just lesser. So it's just warmed up and it can turn over then. So as I said, this video is the second run of this. Apologies for not getting up sooner, but I gave away a bit too much in the last recording, and I didn't want to jeopardize everything I mentioned. So that's what it is. It's as much as I can give without giving away too much. I don't want this channel to ever become, oh, he's, giving away, token information or whatever. I have all the information here, but I just have to be careful. That's all. So just to show you on that, I've taken a screenshot of one of the build manuals for one engine. Let's not mention what it is, and I'll cover it with my hand. Cover all the right parts, so you can see the document. It's all absolutely gospel, the tolerances and how it's done. But in terms of a casual YouTube viewer, like if you're building Formula One engines, you're not getting your information on YouTube, hopefully. But in terms of a casual viewer, it'll give you enough information to know that they're not lock solid, how they're built in terms of tolerances, the huge database that supports them behind the scenes that never gets mentioned, and hopefully if you're down the pub you can talk to the guy that walked out that kept saying that they were lock solid. So you have a bit more information now to say that actually they're not, and here you go. Show them this, but or her. But yeah, hopefully that wraps up this light touch on F1 engine assembly and what's involved. Now, obviously, this channel is going to go on for years. I'm going to cover many other things, but that's just a quick briefing without getting too much into it. And apologies to anyone that has got bored off their face. It's a very boring video, this. I know that. There's been no shiny parts, but what I have over there is the DFV cylinder head, which we'll be tackling next, along with the V10 oil squirter, which I have to post, which yeah, that's coming a while, but it's all ready to go, so I'll get that up soon as well. But I'm going to put preference on the DFV cylinder head, which is right over there, and it's going to be epic. So chat soon in episode 19, I think. Yeah, let's do it. Thanks guys, and link down below. Buy me coffee. Brown paper isn't cheap. I think so far I've used 40 meters of brown paper, so yeah, if you're feeling generous, you know what to do. If not, sit back, relax, and always stay curious. Have a good one. Take care.